Hello, everyone. Hi, we'll start. Welcome to Introduction to Deep Learning. If you're new here, we have workshops that happen every Thursday at 3 p.m. at the Weaver Science and Engineering Library. And in this workshop, we are going to learn about deep learning. This workshop is brought to you by University of Arizona Data Lab, and we work inside the Data Science Institute. Do look Data Science Institute up because there's a lot of cool projects happening in the data world, and we are always looking for students. So anyway, let's get back to what we were doing last time. So if you remember, we were playing with transformers. And I think I showed you this picture earlier, which is everything right now that you see as a large language model is created from transformers. And these are some of the models which are fundamentally, essentially transformers, including the GPT class. Probably the ones missing here are the ones from Google, like Bard or Llama from Meta. But they are all built on one single thing known as transformers. And if you learn transformers, you can learn all of these essentially. It's just a matter of having enough resources to train them. In fact, if you want to put some numbers on it, years, basically, transformers came out in around 2017, and that is in 2018, GPT started the very first version. Then we had GPT-2, T5, and all these things across the years. And like I said, the only difference is these models are bigger than each other as you progress more in time, but fundamentally they are all transformers, which is why we are learning transformers in this class. So candy time. And I know these guys come to the in-person classes only because they love candies. So people online, if you guys need a motivation to come in person, we give out free candies. Either way, this is the question. How does transformer and LLMs, how do they know all this stuff? People online, either you can unmute yourself and speak up or just reply in chat. Okay, people in person, they don't want the candies because they're not answering. So how do all these LLMs know all these stuff?
You say stuff.
Anything, you ask ChatGPT anything, it has an answer for you, good or bad. Either way, it knows, it's aware of almost everything on Earth. How does it know that? Okay, so you're saying we are breaking sentences down, but just breaking them down is not learning. So what is learning? So they are learning something. Okay, Katie says the neural network is learning. Okay. There is a neural network, of course, in all these models, but what is the meaning of a neural network learning?
It's able to generalize based on the given examples.
Testing.
Oh, perfect. Got it, Carlos. Yeah. Okay, so people online, you can mute that. That's fine. I don't think with my accent, LLM, you can close that. I'm hearing it here.
Oh.
Yeah, I don't think with my accent, LLM is going to understand what I'm saying. It does? Okay. Anyway, coming back to our question, how do these things learn? How do these neural networks learn anyway? I thought somebody was going to unmute themselves and speak.
Yeah, I was just saying that they're able to generalize based on the given examples.
Yeah, I agree. But my question is, how do they learn?
Well, they have so much data about sequences of words that they know how, like, which word is likely to follow from another word, and
Okay, so you are
question.
saying essentially they know the frequency of the words, and all that is happening is a complex mathematical calculation behind the scenes, which is looking at the frequency, is it?
I think partially at least that's
Okay,
what's
fair. Okay, yeah. Even Manas had an answer which says I don't think it is about learning, it is about understanding the context. So yes, so far what we have seen is the machine is learning from context, yes, but what is the math behind it? So how does it work? Like, how do you explain to your grandmother what is machine learning? If you guys were in the previous class, you saw some forms of machine learning, say your SVD, right? How is it learning? Something similar to that, how is neural network learning? Somebody said neurons, right? Candy. No idea. No candy. Okay, no candy. All right. So let's see today, how do these things learn? So first, you are all right. It's trained on large amount of text. On top of that, it does something known as supervised training initially. So which means that not only do we take the texts from all these websites on internet, what it is doing is what humans were doing initially is to give also the label for it. Now, what do I mean by the label? If there is a sentence which says, I love this movie, so there will be a human being sitting and adding a label to it, which is, in this case, the sentiment is positive. So that is how all this training started initially, because if you think about learning, you need to learn something and then only can you generalize or extend it, right? So earlier, we were feeding these language models. Here is the data, and here is a sentiment. I love this movie, and we are telling it its sentiment is positive. Now, we give it another sentence, which probably don't even have the same words, right? Maybe the sentence is, I kind of like the movie. So movie is the only thing that is common there. So the tricky part here is Transformers has not seen these words before, but it is able to generalize and even understand the fact that this new sentence, which is I like the movie, is also has a positive sentiment. So think about it. Like if I tell the machine, okay, we have a hash table, here is the text, here is the label, the sentiment is positive, right? The sentence is I love the movie. Next time you ask a hash table, what is the sentiment for I love the movie? It is going to reply back to you, yeah, my value is positive. But that is the neat and beautiful thing of transformers, that it works on unseen data. Because if not, we wouldn't need these kind of large language models or neural networks, right? We could just store everything in some kind of a database, could be hash table, could be SQL database, and retrieve exactly the same question. But this was the huge paradigm shift when people said, okay, hold on, you're learning something on one side, and I don't want you to repeat exactly what I taught you. I want you to be able to generalize to things you have not seen before. So if you think about it, that is a very hard task. So it's almost like you're telling a baby, hey, this is your mom, this is your dad. Do they love each other? And the baby is like, I don't know what the word love means, right? So where is it going to learn all these new things from? Same thing, same idea. How do we teach machines to think outside the box or outside something what it has already learned? So there are a few ways of doing this. The very first stage of any large language model or transformer training is known as pre-training. And you guys were right. Pre-training is essentially you take the whole internet, give it to the large language model. But then, wait, the whole internet doesn't have labels, right? Nobody's going to sit and add to every sentence, this is positive or negative, for examples. So how do they do that? What? Maybe the data is pre-segregated, like a human being sat down and segregated the data into positive and negative. They're what? Who is they? Like some humans are doing it or the machine is doing it? Almost there. I'll give you a candy anyway. So any answers from online? My question was, I just told you everything is learned from the label, but these large language models suddenly have no, it's just trained on the whole internet. So who is going to tell it what does this sentence, what is the sentiment of this sentence, if nothing else? Any answers? In person, online? Okay, Akash says the learning is unsupervised. And you are right. That is exactly what happens. So that's why I wanted to introduce something known as unsupervised learning. So let's see if I can keep your chat window also there. So unsupervised learning is this other paradigm where machine learning people said, sure, we can sit down and label all the sentences in the world, but that's not a feasible task. Nobody is going to be able to do that. We want a machine which is able to learn by itself, right? So some of the architectures which we are using is like this. We start with a base model, which is probably transformers in almost all cases. We give it a large data corpus, tons of days of training. But more importantly, what is the exact methodology that it uses to train? One is called causal language modeling, which is simple. Initially, when we give this machine the word my and tell it, okay, even before that, we first give it all the sentences, break it down into tokens, like we saw that last time, which includes my name is Sylvain, right? And next time, we just ask, tell me what is a word that's going to come after my. Okay, so the machine says, as per the frequency, the word which is going to come is name. All right. So we feed the my name back into it and say, if I tell you my name, what is the word that comes next to it? So the machine says, my name is the next word. And the most important part is step 2 becomes the label for step 1. So essentially, we are saying this data you generate is essentially what we are going to give it back to the model itself to learn. So it's simply learning what is the next word that's going to come with all these sentences. They also do this concept called mass language modeling, where they take a sentence, kind of the same thing as before, but instead of asking it to generate one word at a time, you mask a word at a time and do that for all like a tons of data in the internet. And then the machine is supposed to say, take a guess. My blank is Sylvain. And the machine says, maybe my dog is Sylvain. And then you say, no, remember the gold sentence, my name is Sylvain. Like, oh, my name is Sylvain. So it learns that. So we are in a way using the same data itself to make the machine train on itself. See, we already have the sentence and all we are doing is masking it and giving it back to the model. So great, but what are some of the problems with current LLMs? If you have played with GPT, have you found any problems? Hallucinations, okay, fair. That's okay. We have a virtual candy coming your way, Katie. You should be in person. Anyway, anything else you guys have faced on GPT? Okay, so you're saying if you ask a question and you even tell it that this is not right, it's gonna tell you, oh, sure, I'll take it into consideration, but it doesn't do it. In fact, I don't know if you guys have noticed, if you ask the same question twice, you get a different kind of answer. So these are all inherent problems, but let me ask you one more thing. Can you build your own GPT at home? Let's say I give you all the neural networks, the software component is ready to go. Can you train it at home? Okay, Akash says no. Christopher, that's an amazing point. Privacy and security. You actually brought up a very interesting point. So we will show you something which fixes that. So, but my question is still the same, which is, why are we relying on a few companies like Google or OpenAI to create this ChatGPT? I mean, I can show you the code to ChatGPT today. You just have to GitHub fork. But what is it? Can you run it at home? Okay. And Katie says it's computationally expensive. Correct. So that is the point I'm trying to make, right? So these models are so huge that we as laymen, we don't have the resources to run this. And as an aside, University of Arizona does, and we just created one world's first free chat GPT. I'll talk about that in a second. So this is the amount of data. Yeah, okay. Akash says, I think GPT-4 cost is 110 million to train. Yes. So if you sheerly look at this graph, the x-axis is each of the latest models, and the y-axis is number of parameters. Essentially, you can call it like parameters is basically number of neurons, but that simply means the amount of resources we just want it to train. Like resources could be time, money, GPU, CPU, and in fact, I don't know if you guys know that these days there are ships of GPU, like literally ships in the ocean, which is with GPU, because the heat produced is so huge that nothing on the land could cool it. So Google said, let's hire a ship. Its bottom is always wet, so should be able to cool it, right? So that is the sheer amount of resources we are throwing at these machines in terms of GPU cycles, time, etc. And more importantly, these machines take a long time to train. And the reason for that is all these machines, I'm going to maybe move this here. I cannot look at the chat window at the same time. Okay, so this is a graph which shows the sheer amount of carbon dioxide emissions. So the fact that these machines take such a long time and resources is kind of translating to the amount of carbon that is produced in the atmosphere. So if you look at it, the first line says round trip New York to San Francisco, one passenger takes only 900 kilogram of carbon dioxide emissions, while a state-of-the-art LLM training needs 75,200, creates 75,200 carbon emissions. So altogether, it's a mess, if you ask me. Sure, there are only a few companies doing it, but which brings two major things. One is now you're monopolized by exactly two companies in the world who have the resources to run this. You cannot train it on your own. And two, we are anyway adding so much carbon dioxide emission, not to mention the fact that we want to keep these machines running for at least a month. That's what it takes to train a GPT, because it's training on the whole internet. So do you have a machine which can run for the whole month? Probably not. Not everybody has it at home, right? Especially with heavy GPUs. Oh, we have it at UFA and it's free for everyone. I'll talk about it soon, maybe today or in the next class. So then the question is, if you don't have the resources to train the LLM at home, how can we train it to work on your data? So sure, these LLMs are trained on everything under the sun, but let's say you are a physician or a researcher who has a database of rare diseases, and you are the only one who has the database on Earth because it's very privacy protected and stuff like that, right? Because you are a doctor, you just got these results from all the patients you are treating. Now you want to train a large language model only on this data, but you don't have the resources clearly, right? How do you do that? Okay, Katie says use a beefy laptop, PC, or via cloud. Sure. You can train it on API. You can train it on using an API of ChatGPT. Okay. But what if I don't want the data to leave my premises? Because it's medical data, it's very sensitive. I want my own version of GPT which can answer questions on that data. How can you do that? Okay, Akash says you fine tune it on your data. Perfect. So that is what I was looking for. Akash, maybe next class, if you come to the class and tell me you are the one who answered all these questions, you will get extra candies for the previous class also. Anyway, so the answer is what we call transfer learning. And the idea is all the knowledge that these pre-trained, in this case, it's a CNN, it could probably be a large language model. So let's say this large language model was trained to identify cats and dogs. Then, of course, it's the same case as we had in like a hash table, right? You give the picture of cat and the hash table is going to tell you, yeah, it's a cat. But now if you ask the same machine, here's a car and a truck. What is this? It's going to say it's a cat. Or it's going to say it's a dog because it doesn't know anything else. The hash table doesn't know anything else other than cat or dog. So which is the initial question I asked? If you are trained on one thing, how do you make it generalize? How do you make it to generalize to identify car or a truck, which is, it has never seen a car before, right? So there is something fundamentally, at a fundamental level, between cats and cars, dogs and truck, maybe images, right? So the whole idea in machine learning is there is something fundamentally deep inside. There's a pattern between all the images, which we cannot see, but the machine is able to see, right? It breaks it down to such, not even pixels, it's even much more minor level than pixel, but there is a pattern. In fact, the assumption is there is a single algorithm which created all the images in the world. And with that is exactly what we're trying to get to. If this machine can just look at train on cats and dogs, but if it has never trained on a car or a truck, and if you just give it a picture of a car or a truck and it answers you correctly, that is brilliant, right? Because it has never seen it before. Do you think that's brilliant? That's how these guys are doing it. So how do they do that? So it's called transferring the learning. It's a very huge research topic. And this is the whole idea. Work on something which you have not seen before. So that is one aspect. Another aspect is known as fine tuning, where we take a pre-trained language model, like let's say GPT. GPT is probably a bad example because you can fine tune it, but your data is going to leave your premises. Let's say you have Llama, and you have the computing resources to train it locally on your machine, on your premises. Then yes, we use something called fine tuning, which is nothing but you take your rare diseases database, give it to the same model, and essentially, if you open a GPT and look at the neural network, all these neurons have some weights, maybe 3 trillion neurons. All of them have some weights it has learned. All you are doing when fine tuning is exactly tuning a car. You take a spanner and you're just tightening a couple of neurons here and there to make it focused on the rare disease data set only I have. That's called fine tuning. So we will learn all that in this class. But what happened was when this was the original idea a year ago, people said, okay, sure, let's fine tune things on our own local data. But then not everybody has that kind of resources to train an entire GPT-like network, right? Maybe corporates do, especially academia. As a student, you cannot. So then people invented something new, which is known as retrieval augmented generation. So instead of fine tuning, what it does is, sure, here's the GPT, which is trained on everything under the sun. But now, instead of opening the GPT and tuning the neurons, I am going to give you a database of my, let's say, the rare diseases, and I'm just going to retrieve stuff from it. There's no more training. And retrieval, if you want a simple example for retrieval, it's something you know as Google. Google search is the world's best retrieval mechanism. You ask anything, it can quickly go retrieve the data and bring back to you. So people started leveraging that technology and used it for querying a new data set. So then at that point, you are not fine tuning the whole data or the whole GPT, but you're retrieving data from it. So we did not need such amount of huge resources. So with that, I want to introduce you to our in-house chatbot, which we built in a month. This is probably going to get attached to D2L pretty soon as a chatbot, which will work on your course material. And what this is able to do is we took an open source model like Llama and attached retrieval augmented generation to it. And so, for example, if you're a student who wants to ask questions about only the class materials, you or the instructor can upload the class materials and the chatbot can answer questions for you. But if you ask it anything outside it, like this is how it looks like. So you can pick whatever course you want. And if you ask anything outside it, it says, nope, I'm not allowed to answer anything outside it. And the most interesting thing of this bot we just created is that it's completely in premises, on premises. Your training happens right here at University of Arizona, and we ensure that the data is not going anywhere. More importantly, privacy and security. So no LLM right now has privacy or security. But right now we attached it to the D2L concept. So every student who logs in with the D2L shibboleth is restricted to that data. Like now somebody's authenticating you that you are the only person, the students in the class and the instructor are the only people on earth who will see this chatbot answering questions. So yes, not to brag, but this is big. This is probably going to be a next big thing because nobody has the security attached to any of the chatbots minimally. And this is completely trained in-house. In this class, we will learn how to train a neural network, and eventually you will also build your own personal chatbot on your own data. So what are some kind of tasks that these LLMs, okay, you trained it, and let's say, so what was the task we did last week? What were we using the large language model for? Remember, we went to Hugging Face, we were pip install transformers. What was the task? Okay, nobody remembers from the last class. What? Okay, perfect. Sentiment analysis. Yes, somebody answered on chat that it is sentiment analysis. Correct. So we were doing sentiment analysis. Is that the only thing these LLMs can do? Okay, it can do text generation. Yeah, we also saw text generation. So yeah, so there are what we call downstream NLP tasks using transformers. You can have multiple choice questions. You can have question answering, which of course is known as chatbot. But technically, these are all separate tasks in natural language processing. So sequence classification, et cetera, et cetera. But now is the tricky question. What is a trick from deep inside? How are these things generalizing it? Remember, I just told you, you can train it on pictures of cats and dogs, but if you ask it, or if you give it a picture of a car or a truck, it can reply correctly. How does that magic happen? Take a guess. What might be happening there? Online, anybody? Like, what do you mean by learning? Sure, we gave it everything to neural networks, but at the end of the day, these are machines which understand only 0 and 1. So we need some kind of a logical step to explain it. And how are we doing it, right? How are we telling the neural networks, these are the weights you need to learn? And the answer is, we'll just look at quick math, nothing scary, I can promise. You've seen this before, which is, of course, input layer. We have hidden layers. Initially, the machine just randomly predicts a value, and we say, no, that's wrong. Here is the right answer. You go backwards. And we saw the example that the machine can do it unsupervised, which is my blank is Sylvain, and initially it says my dog is Sylvain, but then we say, look at the golden data. Oh, then it says, oh, my name is Sylvain, fine. So it finds the difference and you back propagate it. So this cycle, it's known as the training cycle. So essentially what happens is you give it all these huge text, the neural network predicts something, and we calculate mathematically something known as loss. And the definition of loss is how close is my prediction to the goal value. So my as in the LLM's prediction. So in this case, the first prediction LLM did was my dog is Sylvain. And we say, okay, let's take all the words there. Let's add it onto a vector. Let's post it. I'll give you the vector of that sentence. I'll give you the vector of the original sentence, which is my name is Sylvain. And the angle of difference between these two sentences becomes the loss. This is a very, very rough, crude explanation of how loss works. But in general, that's all it happens. Like you find if you compare with the goals labels, supervised or unsupervised, you do back propagation. And this happens for like trillions and millions of what we call epochs. Essentially, this feed forward, backward thingy, it keeps happening for a ton of times. Because one, the data is huge, but after one epoch, the machine takes the whole internet and shuffles it around. It does it in batches, which is what we call batches. And once you shuffle the data around, it's not seeing the same sentence at the same time. Maybe the first time it saw my name is Sylvain was the first sentence, but this time it is actually seeing that as the 20th sentence. Believe it or not, that makes a big difference to the machine. The order in which you give the data, which means these machines have this nice vision of something, the actual mental model behind this sentence, the meaning. So it is able to identify the meaning behind these sentences, the meaning behind a cat, and it's able to extrapolate that to a truck. So imagine if your kid has only seen cats and you suddenly show it a car, kid has no idea what car is. But the beauty of this is this picture here. Oops, terrible graphics, but let me see. I'll explain what this is. So the basic assumption here is all the meanings in the world are created using one single function, right? So somebody, maybe you call it God, divine, whatever, but the meanings all are coming from one single point. That is the lowest point in the graph. If you look at the graph, it's like there are mountains and there is a lowest point. So our goal, so mountains might be the first mountain is cat, second mountain is dog, but all these mountains come back to the same valley. And the idea is that if you go to the valley, then you know the answer to everything on earth. So then people start asking, okay, can we make the machines go to that valley? And that is how we have large language models. So what we are not realizing is these large language models are seeing something which humans cannot see. There is an underlying pattern which generated all these words. And at that deep level, you can think of it like an inverted pyramid. Inverted pyramid, all the big words in the world are at the top, which is now a big foundation. But at the core, at the tip of the pyramid, there's something very nice sitting there, which contains the whole world meanings. So our goal was to send the machine there because we cannot go, we cannot imagine it, but can we make the machine slowly get down there? That is all neural networks is, that is machine learning. So then there is this whole idea of, if you are given, let's say, a data set of 100 label sentences, you train it on a part of it. It's usually 80% of the data set. And then we separate the rest of the 20% into validation and test. For example, if you have the pictures of cat, that will be part of the training data set. In the validation data set will be the picture of a truck. So while training, initially, we give it a picture of cat and we tell it's a cat, sure. But meanwhile, the very first step, we also ask, hey, here's a picture of a truck. What do you think this is? The machine says, I only know cat, must be cat. So the very first question, it's going to do terribly bad. But then So that truck is sitting inside the validation slice. And then we find the loss and backpropagate it. And this happens for trillions and whatever number is after trillion so many times that eventually the machine somehow distills its knowledge into that point where all meanings are one. All right, enough of theory. Let's do some hands-on. So we are going to work with an example data set. It's called Microsoft Paraphrase Research Corpus. And the idea is this corpus or data set has some sentences like this. The first sentence is, Amrosi accused his brother, whom he called the witness, of deliberately distorting his evidence. And the second sentence is, referring to him as only the witness, Amrosi accused his brother of deliberately distorting his evidence. Now, when you as a human, when you are given these two sentences, you have the mental ability to infer that both these sentences are exactly the same. The machine does not, because inference is a very, very, very amazing capability of human brain. If I can give you just these sentences and the meaning of these words, how do you, if the sentence is formed in a different way, how do you even have the capacity to tell that these are the same? So this was the whole idea when I told you about shuffling the sentences. We shuffle the sentence and give it to the machine again. And slowly machine is gonna, and the label here is, you can see on the right side, it's equivalent. We are saying, yeah, these two sentences are equivalent. And look at the second one. The sentence is Yucaipa owned Dominick's before selling the chain to Safeway in 1998 for 2.5 billion. And the other sentence too is Yucaipa bought Dominick's in 1995 for 693 billion and sold it to Safeway in 1998. So you can see that the numbers are different because this guy bought it for 693 million and is selling for at 1.8 billion. So we label it, we as in humans label is, this is not equivalent. And that's all we did. We labeled these a bunch of sentences like this, 5.8K, 5,800 sentences, and gave it to the machine. And the machine actually understood what is inference just by two sentences which are equivalent, not equivalent, just positive and negative examples. That is the brilliance of it. And now we are going to do it ourselves. Let's go to github.com/UA data lab. Let's the window here. Okay, are you guys here? Go to repositories, DL workshops, lecture 3, fine tuning, and click on full training MRPC end to end. Open in Colab. Okay, since we don't have much time, we'll probably just, let's see. We'll have create same thing as last time, new notebook. Okay, let's start. Wake up, wake up, wake up. All right. First thing you do is, of course, click to install transformers. But this time I want you to install some more stuff. Click to install datasets and pip install transformers torch. And torch is essentially PyTorch, which is like a framework created by Facebook when it was Facebook, on which all these machine learning models run. So let it install it. I'm assuming you guys have a Hugging Face login, or rather if it's installing, it automatically is logged into Hugging Face. So while it's doing that, let's see if it's me. I'm gonna need them, so let's wait until that's installed. I'm assuming you guys are also following with me. If you have questions, please speak up. All right, I'm assuming it's got installed for you also. Next thing we're gonna do is from datasets import load underscore dataset. So it's just a function which is part of the datasets library. And you might remember this from transformers, import auto tokenizer. We did this last time. We also import something called data collator. And these are all, like I said, at this point, I can hand you this code and tell you, go read on this, which is essentially how computer science works these days. But it's important we understand what these things specifically do. So data collator with padding is a class which does magic on essentially the sentences. Remember when we were tokenizing it, and if one sentence was longer than the other, we wanted to do padding, which is like fill it up with zeros. And why are we doing it? Because at the end of the day, all the calculations or mathematics that happens inside the machine is matrix multiplication. And the only way you can multiply matrix is if it's a matrix. If it's sentences which don't have the same length, that won't be a matrix. So that is why we use something known as padding, which is if the longest sentence in your data set has 10 words, and if there's a sentence which has only 5 words, fill the rest with zeros so that the matrix is not going to error out. Okay, once we have the data sets, what we are going to do is load this data set. And this is what we saw earlier. It belongs to a big data set known as Glue, MRPC. And let me show you Glue Hugging Face. So what happened is, in the world of natural language, all these scientists came up with this set of data sets, which they said, if your machine can pass all these tests, which in this case, for example, this is what we saw, right? If the machine can go through these sentences and correctly answer if they're equivalent or not, your machine is intelligent. And that data set is known as Glue. In fact, there's a new version of it called Super Glue also, if you really want to play around with it. But coming back to our point, which is why we are trying to learn on that data set, because if you can train a machine on that data set, it's like the gold data of learning. And this was created by a lot of linguists and people who thought about these sentences are the best sentences to teach the machine inference. Okay, so next thing is we want to create a name of the model. Let's call it BERT base uncased. To remind you, this was the fundamental transformer model. And we also need a tokenizer, if you remember. Tokenizer is from the auto tokenizer class from _ pre-trained, which we were using last time. And you give the name of the class. Okay, let's run this guy. Okay, it's downloaded the data, it's downloaded all the tokenizers, and this is all ready to go, essentially, at the end of this execution. Okay, another code. Okay, so once we have this, we need to still remember we have to tokenize this data set. So we're going to define a tokenize function. I'm going to feed it with some name. And all we're going to do is return the tokenizer we just created. And this is a data set example of sentence 1. So let's see how this looks like, though. When whatever we got from in the data set, right? What is it called? Raw data set. Let's print raw _ data sets. Okay, it's a dictionary which has sentence 1, sentence 2. Nice. So let's call it, let's see what does this data set have. Train is if you remember one of the partitions. Okay, so it says training data has sentence 1. Okay, so I'm going to ask it, can you also give me what a sentence? Maybe let's give me 1, first element of it. 0, does it work? Okay, there you go. This is the sentence we are looking at. The first sentence is Ambrosi accused his brother, whom we call witness. And if you remember, that's exactly what we were looking at in that. So sure, whatever we downloaded is good. And the reason I told you is we are giving each of these sentences now to the tokenizer and asking it to tokenize it for us. So sentence 1 and sentence 2. And in this case, we are going to call truncation is true, which means if a sentence has more than 10 words, we are going to tell it just cut it out at the number 10. Because remember, at the end of the day, these are matrix multiplications. And to do that, we need to either pad it or pad it to the longest sentence, or just manually decide this is my limit. And I think 10 is by default the number of words. And believe it or not, that works. It's enough for the machine because the machine understands the meaning even if the sentence is not long. Think about it. Is that beautiful? The next thing we're going to do is we're going to run this basically row underscore data sets dot map. We're going to tokenize this, give this essentially running a map on getting this function and running it. We're going to give it batch is true. And we're also, this is our boilerplate, what I call boilerplate, because you probably will use that again and again. This is the data collator we had used. And now we are saying, great, you truncated the longer sentences, but smaller sentences, you have to pad it with 0. And if you want to read more about it, like anything in computer science, Google this, it'll show you the name of the class. And it says data collators will form a batch. So remember, we are feeding it a huge data set, but we are going to give it in small bite-sized pieces known as batches. And that is what the collator will do for you. Right, let's run that. Oh, error. What did I type wrong? Nope, MPA.
Misspelled map.
Map wrong. Okay, MAP. Now what? See, I'm terrible at spelling. Don't they? Truncation is unspelled. All right. I didn't misspell anything this time. All right. It's converting that into small. Okay, let's see what tokenized data set look like. Print tokenized data sets. Okay. It still has all this. So what did we do last time? Train. These are all curiosity stuff, right? So train, it's going to give you this. And let's see, train of 0. Will it work? Okay. I think it's already tokenized. We don't see it. Fair. Okay. So anyway, now let's come to the main part, which is we are gonna. So remember this, one thing in the data set we need to remove is the very first line, which is the headings or labels in this case. So to do that, let's create another. Okay, so I'm just copy pasting it from the code at this point. All it does is remove the columns, sentence 1, sentence 2, and IDX. There you go. Index, basically. Also, I want you to rename the column. We are going to use torch, which is PyTorch, and we are going to use the training for now. Okay, I'm going to speed through a little bit and not type it out this time. I'll just, okay, let's run this guy first. Okay, so the next time, this is the next set of code, and I'll explain what it does. Data loader is essentially a class which takes the data and creates it in a nice bite-sized pieces of what we call batches. And we remember we created the data collator earlier, which is the one it's going to get the data together and see this. This is the beauty of it. Shuffle is equal to true. It means at the end of going through the data set once, just take a big stick and shuffle it around. So this maybe first time, the first sentence pair was Amrosi, blah, blah, blah. Next time, it will be 6 months ago, the IMF, blah, blah, blah. And this is very important because it's almost like you're looking at a Rubik's Cube from different angles, different perspectives. So people discovered that the same set of sentences, if you give it in a different order, the machine is able to distill and learn something from it. Isn't that cool? Just, we would have never thought of it, right? Humans, when we read a bunch of sentences, we'll be like, it doesn't matter the order. You can give it to me in 1, 2, 3 order, 2, 3, 4 order. I'm still going to answer the same thing. But people discovered that simply by shuffling this up, essentially we are telling the machine, hey, look at a different angle and go down all the way to the one single thing which created all this data. Okay, it's the same repeated for evaluation. Remember, we were teaching the machine to learn from cats, but the validation is constantly going to be something it has not seen. And in fact, if you want to print data sets of tokenized data sets, I think it's called validation, right? Maybe. Yep, there you go. So it also has a lot of different sentences, but the key fact is the machine has not seen any of these sentences before. Oh, see, now we see it as tokens. Okay, so if you really wanted to see the text on it, we should probably go row underscore data sets. All right, see, this is a new sentence which we are asking it to predict. It is definitely gonna fail. It's basically, you give it these two sentences, it's gonna randomly pick equivalent or not equivalent, but that's okay. That is needed for us to create a loss function and back propagate it. Now, next one is what we do is for each of the batch, remember there are batches, we're gonna, each of the batch, we are gonna now make it go through this, each of these paths, key value items, right, and make it into a dictionary model. And why are we doing that? Because that's what we are gonna feed into the transformers model. So from transformers, remember, we saw a bunch of tasks in NLP. And this particular task is called sequence classification, which is given these two sentences, classify and tell me if they are equivalent or not. And we are giving it the same checkpoint, which is, if you remember, we call checkpoint as the name of the function, BERT-based name of the model. And we are giving it, hey, there are only two labels, equivalent or non-equivalent. Remember, as far as the machine is concerned, these are two numbers, 0 and 1. It doesn't care. All it is looking for is what is the common pattern because of which this human being thinks this pair of sentences is equivalent or one, while the other pair of sentences is not equivalent. This is machine learning. We are breaking it down into small pieces and telling the machine, hey, here's the mathematical model, you go figure it out. Once you have that, all you have to do is give the batch to the model. If we did this last time, okay, now what? Model. Oh, we didn't run this. Okay, that model is ready to go now. And this is it. Like essentially we are giving it the model and giving the batch saying, hey, tell me what you think, right? And the model says, oh, yeah, this is my first answer. It's going to be wrong, but this is the answer. And remember, last time we saw how to make sense of these, what we call outputs, which essentially looks like it is a tensor. It'll tell you, hey, I'm going to give it so much percentage with the confidence of 0.8306. I'm going to say, oh, this is class 1. And then we tell it, uh-oh, no, that's wrong because you have the gold data with you. Go look again. It's exactly teaching a 6-year-old. So then there is this whole concept called Adam, and what it's called optimizer. And the idea is, remember this picture where I said all the data in the world is created by one single algorithm? This machine, when we slowly bring it down from the mountain, it has this tendency to get stuck in these little valleys, which is not the biggest valley around. So people use this kind of thing called optimization, which essentially means if my machine is going to be stuck in like a local valley, we are going to we're going to give it a push and make it get out of it. So that's what is Adam. Again, a lot of boilerplate stuff. Run Adam. Let's create the next part, which is here is actually where the actual training happened. Remember earlier when we ran through the model, it's just an untrained model. So here we get these training steps. we give it the number of epochs, and epochs is how many times do you want me to go through the entire data. So we just said, okay, go through it first time, shuffle it, go through it again, shuffle it. Right, and let's see. So this point, we probably need also to tell it that, oh, so it does the math and tells you, yeah, if there's 3 epochs and there's so many training steps, so many steps per epoch or batches per epoch, there are going to be so many training steps. Okay, so next is we need to tell it, oh, we are going to use a torch.device, CUDA if it's available. Oh, I didn't show you guys this one. You can actually change runtime type and actually pick a TPU, which is like the most powerful thing that is available right now. Or let's put T4 GPU in Colab itself. But soon this is Colab, and in one of the next classes, we'll show you how to run this all in-house. So while it's going to do that, I'm going to rerun it because we just switched it to GPU. Okay, while it does that, we're almost done. We are at the last cell. All right, should it not be installing? All right, still installing it again. I changed it to GPU, right? Yeah, so it has run this whole thing again, but that's okay. Well, I thought GPUs were supposed to be fast. Michaela, we're gonna need you again to come talk about Cyvers. While it does that, if people are not familiar with it, we have this amazing high performance cluster in our in-house known as Cyvers. Just go read on this. We will soon move from Colab to Cyvers because you get all the state-of-the-art GPUs for free since you're a student of University of Arizona. All right, I think this is all done. The next thing all we are doing is let's train the model. Like, ta-da. So see, the first for loop is for going through the epochs, each of the batches. It's just creating a dictionary of the batches, doing the exact same thing we did earlier, which is here's a sentence, make some predictions. Loss is basically the difference between the gold value and the prediction that the machine made. And dot backward is exactly the back propagation. So this is all is like, yeah, make sure the optimizer steps once, scheduler steps once, standard stuff, okay? So this is your code is gonna run now. And look at this execution pointer. If you can see this, it's actually going through outputs, okay, going back again, predicting an output, calculating the loss, and look at the time it's gonna take, 1,377 steps is gonna be run in 2 minutes. And I actually, how many epochs? We are asking it for 3 epochs. That's it. If you want to wait for 2 minutes, at the end of 2 minutes, you will have a well-trained model, which is ready to go. And you can, this is a model trained only on that particular data set. Also paste here the evaluation if you want to look at it. Just, compare, give it a bunch of data it has not seen before, show me the accuracy. But we need to wait for it to finish training. But that's it. If you guys want to log off, we are at the top of the hour. That's all I wanted to, please go home and play with this. Like, don't even try to memorize this code, but instead just go read what else can you do with this. So you're training, this is your first transformer, all trained by yourself. Tomorrow you want to give it your own personal data set, go for it. In fact, like I said, in a class or two, we will start using Llama on Cyvers, and we will create our own chatbot. All right, people, thank you. Thank you for being there. What is the final output intended to show us? It looks like it measures something. Yeah, so the output is essentially, remember I was telling you this validation set? Its output is exactly the accuracy. If I give you sentences which you have not seen before, how accurate are you? And remember, we are only training it for 3 epochs. People do it for 1,000 and 10,000 epochs. We just gave it 3 because we don't have time to wait or the resources to wait. So it's going to run it only for 3 epochs, but its accuracy will be terrible. It won't be replying correctly. But the trick here is the shuffling. You run it for so many more times and keep shuffling the data. The machine slowly starts to somehow figure out the pattern between all the generation. Okay, I'm probably going to wait for another 10 seconds and see if we have a Habemus Papam, we have a Pope. All right, the model is turned. Let's try evaluating it. What did I do? No module named evaluate. All right, that's weird. All right, we'll have to figure this out some other time. We're out of time. I don't know where evaluate was before. Did I probably one of the classes which I haven't installed? But yeah, just try it. I'll change this in the code before I upload. What is this? What class is this? Install. Install evaluate. Yep. All right, we had not installed pip install evaluate. So that needs to change. All right, evaluate is done. So you're going to see how good the model is when it tried after this. Okay, not bad. It has 86% accuracy just by training it on three epochs. It gives you an accuracy of 86. So it's a good model. From here on, pushing the accuracy will be very tough. That's why we need to run it for 10,000 times maybe. And before the model really goes into the 90s. Yeah, just ignore what F1 is for now. If you don't know, it's okay. All right, guys, thank you. Thank you for listening.